Okay. So max Heapify. Remember what max Heapify is. It's like if the only violation of the heap property in a subtree is at its root. Okay, so we need to do something about it to correct it. Okay, so to be exact, okay, if element AI violates the max heap property, okay, then we try to correct this issue by pushing the element AI down the tree, okay, making the subtree rooted at index I at max heap. Let's look at what happens and what exactly happened here. Okay, so for example, let's take a look at this particular subtree here. This subtree. I mean, the number on the by the side by the node represent the index, okay, and the number inside the node represent its key, okay. So you can see that only this node, okay. So this node is the one that violate the max heap property, right? Because 4 obviously is not larger than, well, 40 is not larger than 7 either. Okay, so what happens is that, okay, we, when we call max Heapify A2, okay, why is 2? Because it's the index where we want to correct this issue, okay, and so we need to push this 4 down, push down to the right, to where it should be located. So you can see that, okay, what happens is that you compare 4 with its 2 children, and then you promote the larger children to the top. Okay, so in this case, okay, 14, 7. 14 obviously is larger than 4, so we should do a swap here. Okay, so we put 14 here, and the 4 becomes at this location, right? But it's not done yet. Okay, it's not done yet. We need to further check if there's a violation here. If there's a violation, we need to keep doing this thing, okay, until no violation can be found. So in this case, 4 is bigger than 2. That's good, but it's not any bigger than 8, right? So we need to, again, promote the larger value of its children to the top. Okay, we need to do a swap between 4 and 8. So eventually, it's going to be like this. So how much time does it take? Well, because we are doing a swap here, right? So, of course, we also need to compare, like, this node with like 2 children, compare this node with 2 children. But basically, all the at one level, the number of operations at one level is bounded by a constant amount of time, right? 2 comparisons and possibly 1 swap, right? So it's going to be constant times, well, the height, right? The height. So in here it's like this will be 2 level. So because this whole tree is bounded by log n, right? The height of this tree is bounded by log n. So the max Heapify, okay, complexity is big O log n, right? Any question with that? Should be pretty straightforward, right? Okay. then. Okay, this is a pseudocode for what we just did. Okay, so this like we just basically like compare the node with the left child. Okay, and then we compare with the right child. Okay, basically you just find the largest one, and then do a swap. Okay, and then we recursively call, making a recursive call to its children, and because like we may need to do additional swap. Okay, so the whole thing is, this is just what I was doing previously. Okay, so this max heapify fix one issue, right? One issue. If that node is the only one that has this violation. How about build max heap? In build max heap, basically we need to we are given an unsorted array. So no node is assumed to satisfy like a heap property. Okay, in this subtree, in this binary tree. Okay, so what do we do? Basically, we will call the max heapify multiple times. What happens is that you see, in the build max heap, it's very simple. For I from n divided by 2 to 1, okay, so down to 1, okay, we do max heapify. Okay, and with this loop, very simply, we are able to fix, the whole array to make it a heap, max heap. Why? First, why do we need to start from n divided by 2? Because any index higher than n divided by 2 has no children, right? Has no child. Okay? If a node has no child, okay, if you only look at that node as a subtree, it has no way to violate the max heap property, right? 如果你就只有一个节点，你怎么可能会违反那个 max heap 的那个 property？ 因为那个 max heap property 是说你的这个节点的 key 要小于你的某一个小孩的 key， 对不对？那你没有小孩怎么小？不可能嘛，对不对？所以当你是 leaf node 的时候，你根本不用担心 violation。Okay, so we start from n divided by 2 because that's the first node that has, children, has child, at least one child. Okay, so okay, and then in other words, it's kind of like this. We start from here, we correct it, make this part a max heap, and then here we correct it to make this part a heap, a max heap. Correct this one, and then correct. And when we get to this point, okay, because everything below has been collected. So we only need to fix this one, right? So we finish this subtree, and again, for the similar reason, okay, all these subtrees are done. So we fix this node to make this one max heap, and then we go back to the root to make the whole tree a max heap, right? So this is a very, very easy or like very straightforward algorithm to create a heap from an unsorted array. Okay. So how about the time? What's the time complexity here? If you look at this for loop, you would have thought like because we run this loop, roughly n divided by 2 times, right? We run this loop n divided by 2 times. And the max Hebify, as I said in the previous slide here, is log n. So the a simple analysis will tell you the time complexity is big O n log n. Is it correct? Is it correct? How many of you think it's correct? Because it's big O, I would say it's correct, but it's not a tight bond. It's not a very tight bond. Why? Because when you are at this level, you only need like a constant time, right? Okay, when you are at this level, you need like 2 times the constant amount of like times, and so at a different level, the number of like operations will be different. It depends on the height of the node, right? The max Hebify operation is dependent to the height of your node, right? If the node is closer to the leaf node, then the number of operations really is not that much, right? It's not that many. Okay, so in reality, we can observe Maxify take big O1 for time for nodes that are 1 level above the leaves, and in general, big OL for nodes that are L levels above the leaves. Is that right? Is that right? So we have n divided by 4 nodes with level 1. Okay, level 1. When I say level 1, is this one, this level. And n divided by 8 with level 2, with here. And so on. So what really happened for this max heap, okay, build max heap, what we are actually doing is something like this. N divided by 4 times 1c plus n divided by 8 times 2c plus n divided by 16 plus times 3c, and so on, up to 1 times log nc, where c represents a constant time. So you can try to rearrange this formula to become like c times 2k. If you try to formulate n divided by 4 as 2k, okay, then replace this one with so it's 2k. This is 2k divided by 2, and so on. Okay, so you can replace this formula with this one. Is it good? Is it good? This term, this one, is actually bounded by a constant. Can you tell that? 你能够知道说这个东西是被常数给绑得住吗？Take a closer look. The top, what should I say? Like the denominator, okay, 就是分母啦，对不对？分子 is increase from 1 to k plus 1, and denominator increase exponentially, 对不对？就是分子是等差上升，分母是等比上升，对不对？对，这个东西你们应该高中在做那个数列的时候，应该都有做过有类似像这样子的东西嘛，对不对？对，所以说这个东西你自己去说说看，这个东西其实是不会太难哦。那这个东西是这个 bracket 里面是 bounded by constant， 因为这个是 because this is bounded by constant, so the whole thing okay, would be big O n. Okay, because 2k, as I said, represent n divided by 4. C is a constant, so you don't count that. So it's basically big O n. So that max heapify only take linear time. And you are able to put the like unsorted array into a max heap. Okay? So is it good? 大家可以接受哦。Okay. Then, this is a demo for build max heap. So you can see that 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. Okay, it is obviously unsorted list of numbers. Okay, so we try to do the build max heap. So so we start from n divided by 2, right? So the number of the largest index is 10. So n divided by 2 is 5. So we start from 5. So this one we see, oh, it violated the heap property, so we do a swap. Okay, and this one again, this one violated the heap property, we do a swap, like swap these two. So it becomes like this, and then we go on to the index 3. So this one again, it violated the heap property, so we need to do a swap. Okay, and then we go to the index 2. Index 2, obviously violated the heap property, so we swap like this one with 16, and then we need to further swap this 1 with 7, so it becomes like this. Finally, we are at the root. So at the root, obviously it violated the heap property, so we swap 4 with 16, and then again 4 violated the heap property here, so we swap like 4 with 14, and then 4 we will swap 4 with 8. So eventually it becomes this one. Right? Should be very easy, right? Should be very easy. So with that in mind, okay, with this build max heap in mind, how do we use this to do the sorting? How do we accomplish heap sort? Okay, it is very straightforward. First, you know that the largest element must appear at the root, right? Because of this recursive definition of the heap. The largest element must appear at the root. In other words, index 1, right? Right? So we just swap that largest element to its rightful place. Where is its rightful place? It's the last one, right? Okay, because we are doing this sorting. Eventually, we want to do sort this number in ascending order. So the largest element should appear at the end. So what happens is that, build a max heap. So we first build a max heap from unordered array, which this one take linear time, and then we find maximum element, which will be located at the first place, and then we swap element an and a1. So we put the largest element at index n, and now we do the max element is at the end of the array, and then we sort of consider n to be consider size of array, consider size of the heap to be n minus 1. Okay, we try to disregard the last element because last element has been sorted, right? So discard node n from heap by decrementing heap size variable. Okay? And then we call max heapify. Okay? Now, root may violate the max heap property, but its children are max heaps. So we run max heapify to fix it. Okay? So that's it. So we basically repeat this loop. Okay? Every time we run this loop, we are able to put one element at its right place. Okay? Okay, the second time, we put the second largest element at the index n minus 1. The third loop, we put the third largest element in a, at the n minus 2 location. And we keep doing that until we finish the sorting. Right? So this is the heap sort. So basically, this is an illustration how heap sort is done. So you can see that. So this is like, what we got. For that, the max heap we got. Previously. So we swap 16 with 1, and then we cut it loose. This part is no longer part of the heap. And then we need to do a max heapify at the index 1. So we fix this. We swap 1 with 14, and we swap 1 with 8. We swap 1 with 4. So it becomes this. And then in the second loop, again, we do a swap. With between 14 and the index 9. And then, okay, so 14, 16 are already sorted. And we put 1 here. So again, we do a max heapify from the index 1. So again, 1 will be swapped with 10. Again, it will be swapped with 9. Okay, so, oops, sorry. So it'll be here. And then we swap 10. We know 10 is the third largest element. So we swap 10 with the index 8. And then, cut it loose. So it's like here. Here. Okay, we swap these two, and then we cut it loose. So 10, 14, 16, they are already sorted. And then the other elements, are not done yet. So 2, again, we need to run heapify. Okay, we do a swap, between 2 and 9, between 2 and 3. So, eventually, okay, keep doing that until the heap is empty. So we will obtain all these elements in the sorted order, in the ascending order. Okay. What is the time complexity of the heap sort? Because we need n iterations. Okay, basically each iteration gives us one sorted element, right? So we have roughly n iteration because, if you argue, it's probably n minus 1 because the last element doesn't need to be, we don't need to do anything, right? It's already sorted. But anyway, so every iteration involves a swap and a max heapify. The swap takes a constant time, but max heapify takes log n. But this one, okay, so, the whole thing will be n log n, right? It's bounded by n log n. Of course, you should also consider, not only this part, but also the build max heap, right? Build max heap. You have to first convert the unsorted array into a heap, max heap first, right? So that cost is linear, as we have discussed earlier. So that linear cost is absorbed by n log n, okay? Because n log n obviously has a higher order than the linear order. Okay, so overall the heap sort complexity is n log n. Okay. It actually has the heap sort actually has many good advantage, because like first obviously it's one of the advanced sorting algorithms, because the time complexity is n log n, right? Okay. Second, okay, if you consider the whole process, the whole heap sort process, you will find that there's no additional space required, right? Unlike merge sort, which require linear additional amount of space, heap sort doesn't require additional space. Okay? And I mean, if you consider all those advanced sorting algorithms, that we have discussed, we only discussed like if you want to make sure your time complexity is guaranteed n log n, then the only two algorithms out there are merge sort and heap sort, right? And we know like merge sort require additional storage space, right? For quick sort, it usually runs faster. Actually, quick sort usually also runs faster than heap sort, but as I said, in some cases, in some very special cases, quick sort could be slower. But heap sort is guaranteed to run, in big O n log n, which is very nice. Okay, so if you want to have a performance guarantee, okay, then and you don't have additional space, then heap sort is the best choice for you. So depending on what situation you encountered, you should choose sorting algorithm differently. This is also a very important concept you should have. I mean, a lot of time, you have multiple different algorithms. You have different choices of algorithms to do one job, but you need to pick like the best, the most suitable algorithm to get the job done. Okay. So that's about it. Oops. Okay, for the heap sort, Okay, and we still have about 10 minutes. Oh, one thing to let you guys know is that next week I will be out of country next week, okay, for a workshop. So this class will still be conducted, but it's going to be conducted online. I believe like my TA already shared the Zoom meeting link with you guys through the EE class. Okay, so if you need, if you don't have Zoom installed on your computer, please download it. Okay, that is like the online course software that we are going to use. Okay, you don't need to register an account, but you do need to download this software. Okay, so this is I just want to remind you. Okay, next week I will not be here. We will not be here. We will be conducting this class online, but we will resume to this in-class lecture the week after the next. Okay? So any question? Yeah, we have a little bit less than 10 minutes. I guess like, well, we don't have enough time to talk about any meaningful stuff anyway. So let's call it a day, okay? And just want to remind you again, I will upload the second homework online. Okay, so please remember to take a look. Okay.